All right, welcome everybody. Today we're going to talk about lesson number 67. We're still in section 9.1, so this is really still the introduction to sequences and series, but today we're going to focus a lot more on sigma notation, which is an extremely important topic for calculus. Notice that I have the homework problems for homework 67 listed here on the front slide, so if you need to jot those down, now would be a good time. If you take a look for 74 to 80 even, it says to use the formulas, and the formulas are what I'm going to show you today. They are meant to be shortcuts, although sometimes they don't really wind up making the problem terribly shorter, but they will be important for future lessons. And then, of course, for that last set there, make sure you're only doing the odd problems. This is a reminder for you about sigma notation. Remember, it's a convenient way of letting us know that we're going to be adding things up. You do, of course, want to pay attention to the index of summation. That, of course, is the variable, typically I, J, K, or N. Then the upper limit of summation tells you what value that you're going to stop adding at, and the lower limit of summation tells you where you're going to start. So that should all be a review of last time. And then here are some examples that are already done for you. Again, a review of what we went over last time. So here you see sigma notation written a little bit differently. They're using the variable x, which again doesn't happen a lot, but I'm kind of getting these examples from all over. Here they're telling you to start at 1. They're telling you to end at 5. They're telling you that the formula is x squared. So you're going to plug in all the values from 1 to 5. You're going to square them and add them up, and that's going to give you a final sum of 55. A little note here at the bottom, the number of terms being added up is always equal to the top value minus the bottom value plus 1. So in this particular example, the top value is 5 minus the bottom value, which is 1. And then plus 1 tells you that you're adding up a total of 5 things, which is why you have 1, 2, 3, 4, 5 things. That might seem obvious, but for a lot of people, when the lower limit of summation is not equal to 1, they have a hard time figuring out how many things to add up. So if you always use the formula of the top number minus the bottom number plus 1, that'll get you the correct value every time. So here's another example. You're being asked to add up all the values from 2 to 4 for 2i plus 3. So here's what you get when you plug in 2, what you plug in 3, and when you plug in 4. If you calculate each of those values and then add them up, you're going to get a total sum of 27. Again, you're going from 2 to 4. So if you wanted to be sure about the number of terms that you're adding up, it's always the top number minus the bottom number plus 1. In this case, that's a total of 3 terms, which is why you're adding up 1, 2, 3 terms. And again, because you're not starting at 1, for some people, they have a hard time looking at 2 to 4 and realizing that there are 3 terms between them. So if you always use this little hint here, I think it's just a great way to check that you're adding up the correct number of things. Another example done for you. So you're adding up all the things from 0 to 5 for the function 2 to the I. If you wanted to be sure how many things that is, you take the top value, which is 5, minus the bottom value, which is 0, and then add 1. That's telling you that you should be adding up 6 different terms. And here they are, 1, 2, 3, 4, 5, 6. Add those together for a total of 63. So that's a review of a bunch of sigma notation problems that are done for you. And really, these are all done, which is what we would call the long way, because you're literally plugging in all of the numbers from the bottom to the top and then adding them up. That is a fine strategy most of the time, particularly in the cases where you're only adding up a handful of things. Let's say that I was asking you to add up 100 different terms or 1,000 different terms. Obviously, that would be kind of silly to write them all out. So there are some shortcuts and some formulas that we're going to go over, starting with the next slide here. These are called the properties of summations, and they're pretty much known as the shortcuts. But something you want to be very careful with is they're only true if the lower limit of summation is in fact 1. So if it's not equal to 1, you can't quite use them. You have to make a compensation, or you have to just kind of list them all out and add them up the same way that we've been doing. So here's the first property of sums, which says if you are trying to add up all the terms from 1 to n of just a constant, then all you have to do is multiply whatever the constant is times the upper limit of summation. Property number 2 says if you are trying to find the sum of a constant times a function, you're able to factor that constant out. Property 3 and 4 kind of go together, and they say that if you're trying to find the sum of two different functions that are being added or two different functions that are being subtracted, you can simply separate them into two or more different sums. So again, these are kind of shortcuts, but to be honest, sometimes they're not really that much shorter than if you were to just plug the numbers in like we've been doing. So they're not required to use at this point, but I would try to use them when it makes sense. So here, take for example, the sum from 1 to 50 of 10. There's no variable in this function, which means that the first term is 10. The second term is 10. The third term is 10. You could list them all out and you would have 50 copies of 10. Obviously, that's a little silly to list out 50 different values. So according to this first summation property here, as long as you're starting at 1, which you are, and going up to some value n, which in this case is 50, if you wanted to find the sum of a constant, you're allowed to simply multiply whatever the constant is times whatever the upper bound is, and that's going to give you a total sum of 500. Maybe that seems obvious to you, and if it does, then great, but technically you are using one of the properties of summation. Take a look here at number 2, or number 5 rather. So you are adding up the values from 4 to 10 of 6. You have to be careful here because of the fact that you are not starting at 1. So you're not allowed to just do 10 times 6 because that would not give you the proper sum. So you have two different options for how you would solve a problem like this. The first way you could solve a problem like this is to rewrite it so that it does start at 1. So you would change this problem as the sum from 1 to 10 of 6. Now, obviously, you can't just change the problem like that because all we want is the sum from 4 to 10. So if you start by rewriting it as the sum from 1 to 10, that would give you too much. So in order to get rid of the extra, you would subtract the parts that you don't want. So if you're only wanting the sum from 4 to 10 and you rewrite it as the sum from 1 to 10, you're then going to subtract off all the values from 1 to 3. Again, take a look at why that works. If you ultimately want the values from 4 to 10, if you first solve for the values from 1 to 10, and then you subtract all the values from 1 to 3, you'll essentially be left with the values from 4 to 10. So now you're going to use that property of summation actually twice. You're going to calculate the first summation, which would be 6 times 10, which would be 60. Then you're going to subtract the second summation, which would be 3 times 6, which would be 18. So that is going to give you a total sum of 42. Another way that you could do this is to look at the problem and realize that 10 minus 4 plus 1 is equal to 7, which means you are adding up 7 terms. Each of those terms is 6, and 7 times 6 is still 42. So technically this way might be a little bit longer, but you are in fact using the properties of summation, where if you did it this way, you're kind of just cheating a little bit. Honestly, either of these options would be fine as long as you could get a total answer of 42. Take a look here, the sum from 2 to 5 of 4i. So if you'll notice 4i, that basically means that every time you plug in a value, you're multiplying it times 4. So if you want to save yourself a step, you're going to use the second property of summation, which says you can factor the 4 out and rewrite it as the sum from 2 to 5 of just I, which means that you're going to leave the 4 out front. And now you're going to plug in all the values from 2 to 5 to I. So 2 plus 3 plus 4 plus 5. If you then go ahead and add up, 2 plus 3 is 5, 5 plus 5 is 10, plus 4 is 14. 4 times 14 is a total of 56. So technically this step here is where you're using one of the properties of summation. Here, you're using the long method by plugging in each of those values. Again, for now, as long as you ultimately get to 56, that's all that matters. Once we get into 9.2, you're going to have to use formulas because instead of asking you to go from 2 to 5, I'm going to ask you to go from 2 to 5,000, which means you certainly aren't going to want to sit there and just plug in each of those values. Consider number 7, you're being asked to find the sum from 4 to 6 of k plus k squared. So this is the third or fourth property of summation, which says if you are taking the sum of more than one function, either being added or subtracted, then you are allowed to break that up into the sum of the first function from 4 to 6 plus the sum of the second function from 4 to 6. So if you go ahead and do the first sum, so from 4 to 6 of k, you're going to be adding 4 plus 5 plus 6 plus, if you add up from 4 to 6 of k squared, that's going to be 16 plus 25 plus 36. Go ahead and add up each of those values, and you're going to get a total sum of 92. Now, again, if you're asking yourself, did that really save me any work by splitting them up? Could I just have plugged in 4 and done 4 plus 16, and then plugged in 5 and got 5 plus 25? The answer is yes. Again, the idea of these being shortcuts is really for harder problems as the chapter progresses. For now, any means for you to get 92 would be fine, as long as you actually get to that answer. So if you are, in fact, adding up the sum of the terms of a finite or infinite sequence, that is called a series. So basically, a series means that you are adding up the terms of a sequence. There are 2 different ways you're going to be asked to do that. You can either be asked to find the sum of a finite sequence, which would mean it's a finite series, or you might be asked to add up all of the terms of an infinite series or an infinite sequence, which would give you an infinite series. So take a look at the notation. If you're doing it in a finite manner, you have to start at 1 and end at a number. Whereas if you're doing it for an infinite sequence, you're going to start at 1 and you're going to end at infinity. If you're only adding up a finite number of terms, that is called an nth partial sum. So if you're adding up the first 6 terms, it would be called the 6th partial sum. If you're adding up the first 10 terms, it would be called the 10th partial sum. So that's just a little bit about vocab and notation. How do you add up the things of an infinite sequence, you might be asking? Well, you can't actually add up an infinite number of things. So you'd be telling me what value it's getting closer and closer and closer to. And remember, of course, that if you're talking about a value that you're getting closer and closer and closer to, that is, of course, the idea of a limit. So if we take a look here at number 8, it's already done for you, and then we'll do one together. So here is the series, which is the sum from 1 to infinity of 3 over 10 to the I. You're first going to find the third partial sum, which means you're adding up the first 3 terms only. And then you're going to find the total sum, which assumes that you would go to infinity. So in order to do part B, you have to start by doing part A. So the third partial sum means that you should rewrite it as the sum from 1 to 3. You're only adding up the first 3 things. So if you're adding up the first 3 things, then in the function, you're going to plug 1 in, you're going to plug 2 in, and you're going to plug 3 in. Notice that the fact that the denominator is 10 is what makes this a very simple problem. You're really only going to be able to do these for problems that have a denominator of 10, at least for the time being. So when you divide 3 by 10, you should, of course, know that that is the terminating decimal, 0.3. When you divide 3 by 10 squared, you're dividing 3 by 100, which means move the decimal point again, which would give you 0.03. This would be 3 divided by 1,000, which would be 0.003. And if you are adding up just those 3 things, you would get the terminating decimal, 0.333. In part B, they're asking you to consider what would happen if you kept on going with this pattern. So if you continue to take the exponent I and make it larger and larger and larger, because it's always going to be a multiple of 10, you're going to continue getting these values here, where each time the decimal point is simply going to move 1 spot to the left. If this process were to occur and repeat to infinity, you would essentially get 0.33333 never ending and never repeating. Well, could you approximate that value? Where is that value going if it's 0.3333 repeating? I think you could pretty accurately say that that is in fact 1/3, and that's kind of the idea of a limit. The fact that you're getting very, 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 very close, you technically aren't ever actually getting to 1/3 because you're going to infinity, but you're getting so close that we feel comfortable in you doing that. Something else you kind of want to notice here, so 0.3333 repeating, you could also think of that as 3 times 0.111111, etc. It's important that you know that 0.111 repeating is always going to be equal to 1/9. In a case like this, 0.33333, I think that everybody knows that that's 1/3. But if you were to get a decimal that you're not as familiar with, you would always want to factor out like this. And as long as you know that 0.11111 is always equal to 1/9, then you would always be able to tell me what that value is approaching. So let's look at a very similar problem. You're finding the sum from 1 to infinity of 5 over 10 to the n. Notice how the variables are kind of changing. I'm using i's and k's and n's. Again, the variable in question will depend on the problem, the book, the internet resource, so you kind of have to be comfortable using all of them. Notice again the fact that the denominator is 10 for now. It has to be, or else this process really wouldn't make sense. So let's go ahead and start by finding the third partial sum. So if you're finding the third partial sum, that means that you are finding the sum just from 1 to 3. So if you are finding the sum just from 1 to 3, your first term is going to be 5 over 10 plus 5 over 10 squared, which is 100, plus 5 over 10 cubed, which is 1,000. You're going to see a very similar thing happen. You're going to see 5 divided by 10, which is going to give you a half or 0.5, plus 5 divided by 100 is 0.05, plus 0.005. And if you're adding up just 3 things, you're going to get 0.1, 2, 3, 5s, ending and terminating. Consider what would happen if you were to go to infinity. If you were to go to infinity, you would continue to keep getting more and more and more 5s. 0.555555, it's possible that offhand you don't know what that fraction is. So if you were to go ahead and factor out the 5, you would get times 0.11111. 0.11111 is always going to be equal to 1/9, which means that the limit of this series would be 5/9. So again, this trick doesn't work unless you have a denominator of 10, but they're going to have to be 10 for the time being, or else it's not going to work. So now I'm kind of asking you to do the reverse of what we've done so far. I am actually going to give you the series written out, and you're going to go ahead and write it for me using sigma notation. So again, here's an example of one that is already done for you. So again, assume that you are starting at the first term unless I tell you otherwise, which means that these would be the first 5 terms. The fact that these are the first 5 terms is how I know to make my lower limit 1 and to make my upper limit 5. You have to choose a variable for these problems unless they tell you which one to pick. I'm personally a K gal, but you can use any variable. I'm going to kind of mix it up a little bit. If the problem or the book tells you to use a specific variable, you should. And certainly by the time we get around to the edge elastic test, I will tell you what variable to choose. But for now, you can choose whichever one you like. Once you realize that you are in fact adding up the first 5 terms, I think it's pretty clearly obvious here that the numerator of your fraction is always 1, and the denominator of your fraction is always the term number, which in this case would just be K. Let's try a couple more where you yourself have to actually decide what the formula will be. So 1, 4, 9, 16, 25. And again, hopefully those values look relatively familiar. This is the first, second, third, fourth, and fifth term. That is how I know that I am finding the sum from the first term to the fifth term. And again, I'm using K, but you could use any variable. What is the actual formula? How does a 1 become a 1, a 2 become a 4, a 3 become a 9? That's our old friend, just the perfect square. So in this case, it would be K squared. Make sure that your variables always match. Okay, if you're using K, make sure they're both K. If you're using I, make sure they're both I. So 1, 2, 3, 4, 5, 6. In number 12 here, you are adding up the first 6 terms. So you are adding up the terms. Let's go ahead and use K again. So you're adding up the terms from 1 to 6. You have to go ahead and figure out what the pattern here is. So it looks like you're adding 5 each time. Constant addition, remember, means that it's linear. So you're always going to try by taking whatever that value is, 5, and multiplying it by whatever the term number is, which in this case would be 5K. Remember, sometimes that's the answer, and if not, you make a compensation. But in this case, 5 times 1 is 5. 5 times 2 is 10, 5 times 3 is 15, so you're getting exactly what you want. Your ability to find these equations, this is similar to what you did on virtual homework number 1. So anybody who was having trouble on virtual homework number 1 finding those equations, you're kind of getting a second round of practice now. Let's try a couple more here in 13 and 14. So this is 1, 2, 3, 4 terms being added up. So you're finding the sum from 1 to 4. Again, looking at this problem, it's pretty clearly a fraction, and the numerator is pretty clearly always a 1. If you're looking at the denominator, 3 becomes a 9, 9 becomes a 27, 27 becomes an 81. It's pretty clear that in the denominator, you're multiplying by 3 each time. Remember that if you're having constant multiplication, that implies that it's an exponential. So you're going to start by rewriting it as 3 to whatever the variable is, in this case, k. Sometimes that's the answer, and if not, then you have to make a compensation. But 3 to the first is 3, squared is 9, cubed is 27. So it looks like that is exactly what I was looking for. Here in number 14, 1, 2, 3, 4, 5. That appears you're adding up the first 5 terms. Let's get a little crazy and use 1 instead. So you're adding up all the terms from 1 to 5. Again, you can pretty clearly see that there is some fraction action going on here. If you take a look at all of the numerators, they are exactly equal to all of the term numbers. So if you're using the variable I, then it looks like your numerator here is simply going to be I. If you look at the relationship between the term number and each of the denominators, it appears that they're always exactly 1 more than whatever the term number is. So again, if your variable is I, then your denominator would be I plus 1. As always, whatever it is you write here, if you want to check that you're right, simply write out the terms in the sequence and hope that they match up. A couple more here. So 9 over 1 plus 1 plus 9 over 1 plus 2. Obviously, this is kind of a strange looking sequence, but you need to write it out in this fashion, or else there would be no way for you to figure out what the pattern is. So it looks like this is the first, second, third term, and then there's a bunch in between. And I think we're fairly confident in the fact that this is the 14th term. So we know that we are adding up the sum from the first term to the 14th term. And again, I'm back to k. That's just kind of my personal preference, but go ahead and choose whatever variable speaks to you. Fraction, numerator of 9. And then I think it's pretty clear that 1 plus k is the pattern going on the bottom. Obviously, on a test or quiz, I could make these problems as easy or as difficult as I want to. So make sure that you do all the homework problems so that you get a mix of the difficulty level that might be expected of you. 1, 2, 3, 4, 5, 6 here, for example, number 16. So looks like we are adding up all the terms from 1 to 6. We again have a fraction. Those numbers at the top, 1, 2, 6, 24, 120, 720, I would hope that at this point, those are kind of getting a little bit familiar. Hopefully you remember that those are in fact the factorials. So the factorials, remember, is when you multiply all of the numbers from wherever you start down to 1. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, and that is in fact 720. 5 factorial is equal to 120, and all of those match up exactly, which means that your numerator would be k factorial. If you haven't gotten familiar with those first couple of values for the factorials, you will as the chapter progresses. Taking a look at the denominators, I think it's pretty clear that each time you are multiplying by 2. Remember that that constant multiplication implies exponential. So you're always going to start by saying whatever that multiplier is raised to an exponent. Sometimes you get lucky and that's right. Sometimes you have to make a compensation. In this case, 2 to the first is 2, squared is 4, cubed is 8, which means that is exactly what you're looking for. So that's the end of the summation talk. And then finally, one last thing I want to talk about, which you actually did see in those first couple of emergency closure days, but this is the idea of a recursive sequence. So that's kind of a new and different vocab word. The idea of a recursive sequence is that you can't find any of the terms of the sequence unless you know the previous term or sometimes a few of the previous terms. The most famous recursive sequence that you probably are familiar with is the Fibonacci sequence. The Fibonacci sequence, to find any term in the sequence, you add together the previous two terms. So what would that look like as an equation? Well, again, in this case, they're assuming that you're starting at the 0th term, which again, we're going to always assume the first term unless I say otherwise. But in this example, they are including the 0th term. So they're telling you that the 0th term is 1. They're telling you that the first term is 1. And then they're telling you to find any other term in the sequence, which we're going to call a sub k. You have to add a sub k minus 2, which means the term 2 spots ahead of it, plus a sub k minus 1 means the term 1 spot ahead of it. So if the 0th term is 1 and the first term is 1, if you want to find the second term, you would have to add together the term that's 2 spots ahead of it plus the term that's 1 spot ahead of it. Oh, sorry. And so in this case, that would be the 0th term plus the first term, which would be 1 plus 1, which is how you would get a value of 2. If you're trying to find the third term, you would have to add together the term that's 2 spots ahead of it plus the term that's 1 spot ahead of it, which in this case would be A1 and A2. That would be 1 plus 2, which would be 3. If you want to find A4, you're going to add the 2 previous terms, which would be 5. If you're going to find A sub 5, you would add together the 2 previous terms, which would be 8, and the pattern would continue. So again, it's very likely that you have seen or heard of the Fibonacci sequence before. It is, of course, the most famous recursive sequence, which means that to find any term, you have to know the term before it, and sometimes you have to know several terms before it. An example a little bit more of what I would be asking you for would be something like this. Write the first 5 terms of the sequence that is defined recursively. So here I'm telling you that the first term is 15, and I'm telling you that to find any term, in this case a sub k plus 1, you would have to find a sub k, which means the term 1 spot ahead of it, plus 3. So you're going to see different kinds of notations for recursion. But again, if you see that magic word, it's telling you recursion. So you kind of know to look carefully at the notation. So if you're trying to find the first 5 terms in the sequence, they're telling you that the first term is simply 15. Then if you look at the formula, they're telling you that to find any term, in this case, they're saying k plus 1, you're going to have to find a sub k, which means the term directly in front of it, and then you're going to add 3. So what that means is that if you're trying to find the second term, you're going to take the term in front of it, and you're going to add 3. So if the first term is 15, to find the second term, you're going to take 15 plus 3, and you're going to get 18. If you wanted to find the third term, you're going to take the term in front of it, which would be a sub 2, and you're going to add 3. So 18 plus 3 would be 21, plus 3 again would be 24, plus 3 again would be 27, and there are the first 5 terms that you're looking for. So it's not that recursion is difficult by any means, but it is something a little bit different. And again, a lot of people just get lost in the notation, so try your best not to do that. Another example here, they're telling you that the first term is 32, and then they're telling you that the relationship between any term, in this case k plus 1, is always equal to 1/2 of the term that directly precedes it. So they're telling you that the first term is equal to 32. If you wanted to find the second term, you're going to take half of the term in front of it, which in this case would be half of A1. Half of 32 is 16. In order to find the third term, you have to do half of the second term, and then the pattern continues. So again, because they're asking you for the first 5 terms, that's exactly what you're looking for. Here are a couple of examples that are done for you already, where they give you the sequence and then they ask you to find the formula. The notation is also a little bit different here. So I'm trying to show you all the different examples of the ways that you could see notation. Notice here that they're using n's instead of k's. And notice that instead of using k and k plus 1, they're using n and n minus 1. So whether they're talking about the term directly after it, which would be k plus 1, or they're talking about the term directly preceding it, which would be k minus 1 or n minus 1, again, I'm fine with you using any of those notations unless the book or the problem specifically asks you for something. So consider 2, 4, 8, 16. If they're telling you that you have to write this as a recursive formula, then you have to write the formula in terms of the previous values. So if you know that the first term in this example is 2, and then to find each of the subsequent terms, you'd be multiplying by 2, the formula that you could be using in general to find any term number would be to multiply 2 times the previous term. So again, what this would mean is that if you wanted to find the fourth term, you would do 2 times the previous term, which would be the third term. And if you were to do 2 times 8, you would in fact get 16. And again, the pattern has to hold for all the values in the sequence. Take a look over here, -8, -1, 6, 13, and 20. It is pretty obvious that you're adding 7 from one term to the next. How do you write that in terms of a recursive formula? Well, in this case, they're using the notation a sub n. So they're saying to find any term in the sequence, you're going to take the term in front of it, which would be a sub n minus 1, and you're going to add 7. So again, what that would mean, let's say, is that you wanted to find the fifth term. That would mean that you're going to take the fourth term, and you're going to add 7. So if you were to do 13 plus 7, you would in fact get 20. 405, 135, 45, 15. If you're trying to find the pattern here, the numbers are clearly going down, and they all appear to be going down by the same factor, which is they're all being multiplied by 1/3. So the fact that they're being multiplied by 1/3 is what tells us that in our formula, to find any value in the sequence, you're going to multiply 1/3 times the previous value. In this next slide, I just want to make it clear that these are all different notations that you could possibly see, all of which would be acceptable and equivalent. So let's say you had 50, 60, 70, 80, 90. And again, there are lots of ways you could write a formula for that sequence, but because they're telling you that you would have to use recursion is how you would know that you would have to write it like this. So notice that 2 of the examples are using the variable k, and 2 of them are using the variables n. And again, it doesn't matter the variable. I think your book uses k's, but you have to be able to do it for any of them. In this example here, they're talking about any term being k plus 1, and they're talking about the previous term being 1 less, which in this case would be k. In this example, they're talking about any term being k, and the term in front of it being 1 less, which would be k minus 1. Again, these two equations are 100% equivalent. Both of them would be acceptable. So I just want to make sure you understand that either of them are acceptable, and then very similar for these two, except for the fact that you're using n's instead of k's.